Hello Stats class, this is lesson 12.1a, the beginning of our last chapter before AP. Oh my goodness. So, inference, as you know, is about looking at a sample and making conclusions or estimates about the population. And this last chapter is inference specifically for linear regression, which we learned about way back in chapter 3. It was about the scatter plots and the lines of fit, which is why your warm-up mostly reviewed chapter 3. So let's just think about that for a minute. We're going to draw a large scatter plot so that we can draw all over it. And we have our x variable down here, explanatory variable. We have our y over here, which is the response variable. And imagine a large population of dots. So I'm going to just draw a lot of dots all over the place. And it's a slight positive trend, but not super strong. Okay? So most of the time, we have this huge population of points that could happen, but we don't actually gather data on all of them. We would just have a sample of points. So like maybe this is in my sample, and this one, I'm just going to pick a few and say these are my sample. And I could take that sample of, so in this case, a very small sample of points, and I could find the line of fit. So if I found the line of fit, it would go something like around in here. That line of fit would be slightly different if I had a different set of points. So the set of points that I choose for my sample makes a difference in my line of fit. This is actually the estimated line of fit. Which comes from the sample. And if I did a different sample, I'd get a slightly different line of fit. So we're going to be working with that and talking about the sample versus the population in this context. You saw that with an experiment in the warm-up, and it could happen with an experiment and being re-randomized like you saw in the warm-up, or it could happen with a sample from a population. So I'm going to talk about sample versus population. And make a little t-table. We have our sample, which gives us the estimated line of fit. And we actually have already learned a lot about those things. We learned to write it as y hat equals a plus bx is the form our book likes to use. And remember that the a is the y-intercept and the b is the slope. And so far, all we've done is look at a sample and find a line of fit from the sample. So this is what we've been doing. But I want to remind you that there's this bigger population happening, that in the bigger population, we have what I would call the true line of fit, which is the line of fit that would happen if we could actually get all the data. If we could gather all the data on all of these points and find the line of fit, we would get the true line of fit. And instead of y hat, we're going to think about this is the predicted y value for a given x. So if we pick a particular x value like this one right here, we're looking at all of these possible y values, and the predicted one is right here, but in the middle of all of this is the mean, which might or might not be the same as the prediction from this particular sample. So maybe the mean's a little lower, maybe it's a little higher, but this is the mean y value for this particular x value. And obviously if I moved x over here, then I'd have a different mean y value and a different mean y value. Put those all together and you get the true line of fit. So the true line of fit is the mean y. And instead of a and b, we're going to use Greek. We're going to use alpha for a, and we're going to use beta for the slope. So this is the Greek letter alpha. This is the Greek letter beta. I know you've seen alpha before in a different context as a significance level. We're not really going to focus on alpha a whole lot in this class. It's the true y-intercept, but we're going to focus on the slope. So it's okay to use the same symbol for alpha. We're mostly focusing on beta, which is the true slope. So that is where we're headed with this. We're going to use what we can do with our sample to predict the population line of fit. And for this class, we're going to keep it simple and focus on the slope. And that means we are using our statistic B to estimate our parameter beta. And remember, the parameter has to do with the population, and the statistic has to do with the sample. We've seen all of that before. Okay, so we're going to do a bunch of stuff, and we're not going to do it all in this first lesson. So there's a lot of stuff I have to tell you. I think for the rest of these notes, we're going to just do the conditions only. And then we'll come back to the rest of the significance test. Actually, we're going to do confidence intervals first, but not today, or not in lesson 12.1a. That'll be 12.1b. We'll start with conditions for inference about slope. So that's the main thing I'm going to teach you today, is how to check the conditions. And then in 12.1b, I'll teach you the rest of the steps involved in the confidence interval, which is actually not very hard because the computer does a lot of it for you. So good news and bad news. The good news is some of these are familiar. The bad news is there's 5 of them instead of 3. Oh dear. That's okay. We're going to do all 5. And the first 2 that I'm going to write down are ones that are the same as what you've been doing. So I bet you could guess the first one. It starts with R. It's random. Yes. I'm so happy to hear that we're still doing a random sample. So it needs to be a random sample of ordered pairs. In other words, it is always paired data that we are dealing with here. And so you have to have an X value and a Y value for each of your data points. That's fine. Or it could be randomly assigned treatments like we saw in the warm-up. And the treatments would be the X value and the Y would be the response variable. And we saw something like that in the warm-up, so I'm not going to worry about that too much. But you check to see if it's random. It's either randomly sampled or randomly assigned. The next one, we usually do normal next. I'm going to put it third for a reason, which I'll tell you in a minute. But the third one or second one, either way, is independent. That's the same as what we've done before. So I'm purposely starting with the easy ones, and I'll come back to the normal because it's a little harder. So independent, it's the same 10% rule that we've done before. The sample size, number of ordered pairs, has to be less than or equal to 10% of your population. It's still called N, and it's still called capital N, so that's all the same. Or you have randomly assigned treatments, and so then you wouldn't have to worry about it for an experiment. So those 2 are familiar. Yay, we already know how to do them. There is also a normal condition, and I put it third because these next 3 all kind of go together. And I'm going to show you a picture that will help with to understand where this is coming from. How in the world can a scatter plot be normal? Let me talk about that. So there's a picture in your book on page 742. I actually printed it so it would be easy to show you on these notes. It looks like this. So what is actually happening, I am not going to try to draw this, and you shouldn't either, but what's actually happening is we are assuming that for each individual X value, there's a normally distributed set of Y values. And for this X value, there's a normal distribution of Y's. And for this X value, there's a normal distribution of Y's. So one of the conditions we're checking is whether this normal assumption is reasonable, and we can do that by looking at the residuals. Because remember, residuals are just how far above and below the line each point is. And if we look at the residuals and see if they look normal, that's what we need to do. So we plot the residuals, and this isn't a residual plot. It's not a scatter plot of residuals. It's a box plot or a histogram or a dot plot. Something like that. Sometimes we use a normal probability plot for this, which we've seen before, but it's a little bit weirder. And we're looking for evidence that the residuals come from a normal distribution. So these three, we're not going to be super picky, but we're going to look to see if any one of these three is not too skewed. And if we're looking at a normal probability plot, remember, we're looking to see if those are approximately linear. So you can check it by any of these methods, but we're looking to see if our residuals fit the idea in our mind, which is this. So this is like a picture that should be in your mind, but you're not going to try and draw that because it's like a three-dimensional weird thing. All right. There are two more, unfortunately, besides these three familiar ones. So the next one is almost too obvious. It has to be linear. We can't do a line of fit if it's not linear. So yes, one of the conditions is you check to see if it looks like it's curved or not. You can do that with either the original scatter plot or a residual scatter plot. And when you look at those, we're just looking to see if it's not curved. We're not super picky about that either. If it's an approximately oval-shaped cloud of points, that is good enough. So we're just looking for one of those plots to be not curved. Or an elliptical cloud if you want to be specific about that shape. And then the last one is also not as obvious, but it goes back to this picture again. When you're looking at these normal curves that happen for every x value, we also want them all to be about the same width, about the same standard deviation on all of them. Because if some of them are really wide and some of them are really narrow, that kind of messes up our calculations. And that sigma is the standard deviation of the residuals, which we've talked about as S before. Sigma is the parameter, and S is the statistic, similar to beta and B or alpha and A. But the idea is these normal curves need to be about the same width or about the same spread on all of them. And so that last condition is called equal variance. And you are looking at the scatter plot to see if it looks like it's evenly spaced above and below the line. So the reason I like to put these three last is all three of these require that you look at a plot of some sort. And there's no other way, like in the means where you could check to see if it's bigger than 30 and then you didn't have to look at the plot. This one you have to look at the plots for all three of these. The good news is usually they give you the plots, and like you'll see this in the homework, they'll give you these plots and say based on these plots are the conditions met. And so you just look at them and describe what you see. So a little bit more about the equal variance. Good variance looks like evenly spread above and below the line. Or on a residual plot, it would look like what you want residual plots to look like, which is evenly scattered and no pattern. So good residual plots and scatter plots look like that. There's an official name for that even spreadness, evenly spaced or whatever. It's called homoscedastic. Equals evenly spaced or evenly spread. I like to think of it as icing on a cake. If you do icing correctly, you have the same amount of icing at each spot on the cake, and you don't have a lot at one end and a little bit at the other end. I mean, I suppose some people might like it that way, but we want it to be evenly spread. So that's homoscedastic. That's the good situation that you're looking for. Bad would be if you have fanned out data. So you could have really small at one end and really big at the other end, like a drumstick or something like that, and your line of fit goes like this. And so it's fanned out. On the residual plot, it would look also fanned out, really big at one end and really small at the other. And it might not be the larger end that's wider. It might be wide at this end and small at that end. So this is fanned out, which is also called heteroscedastic. All right, so we want it to look like this. We don't want it to look like this. Hetero just means the spread is different. And every once in a while I have a gay student who gets really happy that homo is good and hetero is bad in this situation. The book doesn't put them in the same order. These 5 can go in any order you like. You can do random, normal, independent, and then tack on the other 2, which is what I usually do. Or you can do what the book does, which the book calls it liner, so that you can remember all 5, L-I-N-E-R. I don't like doing it in that order because it really bothers me to put random last because that seems so important to me. You do it in whatever order you want as long as you get all 5. And the homework for this first lesson is mostly just checking conditions. They will ask you to look at the graphs and say, does it look like it's evenly spread? Does it look like it's linear? Comment on the graphs and what you see in them as part of your checking conditions. And then in lesson 12.1b, we will go into more details about how to calculate a confidence interval. So that is it for this one.